All right. So we just got through talking about listing. Well, here's a problem that let's use as an example to show maybe there's a better way of going about this counting than just brute force method of counting these out. Now, of course, what I've got here is I've got George on our handout there. George has a problem, and he's wanting to figure out how many different outfits he can make with his shoes and pants and shirts that he has. He's got a green shirt, a red, and a yellow, and a white shirt. He's got Dockers for pants, and he's got a pair of Savan, just a type of pants that I used to own, but jeans. That's his three possible pants that he has to wear. And then he has black and brown, K for black and N for brown, shoes. All right, what I've got here then is the tree diagram showing all the possibilities George has for outfits. He can do his green, red, yellow, white shirt. But with his green shirt, he could wear his Dockers or Savan, or he could wear his jeans. And then for his red shirt, he could wear his Dockers, Savan, or jeans. And for his yellow shirt, he could wear his Dockers, Savan, or jeans. You get the idea. All right. Now, if he wears his Dockers with his green shirt, well, he could wear his black or brown shoes. Same thing if he wears his Savan with green shirt, he could wear his black or brown. So you get the idea. All right. So how many different outfits can George altogether make? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 19, 20, 21, 22, 23, 24? He's got 24 outfits. Like I was saying, though, is there a better way we could do this? Could we get the question down at the bottom of the handout? Could we get the total number of possibilities without using the tree diagram? Hint, look at the number of shirts, which is 3. The number of pants, which is 4. 4 shirts, 3 pants, 2 shoes. Is there any way I could get 24 out of those 3 numbers? And I gave you a big hint right there on the board. What is 4 times 3 times 2? It's 24. Not by coincidence is that matching. Now what we did is, well, if you think about it, here's how this is working. You see, I start out with, let's start off with the shirts, first of all. I started with 4 shirts, okay? So there's 4 here. But doesn't that multiply to 12? Because for each of the 4 shirts, I can branch off of that 3 ways, right? So I can branch off, it's scrolled off the screen there, but I can branch off of it, off the green shirt, 3 ways. I can branch off the red shirt 3 ways, and then 3 ways. So that gives me 12, if you count them all up there. But then, off of each one of those, I branch off 2, or multiply by 2, because I've got the black or brown shoes. So that gets me to the 24. So yeah, it's a multiplying process. You start with 4 shirts, then you put in the 3 pairs of pants. You got 12, then you put in the 2 shoes, that gives you 24. So it's a multiplying process. All right, well, let's take a look. Page 2. On page 2, I give you what this is called. This multiplying process is called the fundamental counting principle. And here's the statement of it. Suppose an event or task consists of multiple parts. If there are R ways to do one part, S ways to do a second part, T ways to do the third part, so on and so forth, then what do? We multiply those parts together. Take the R times the S times the T, and you could go on and on from there. Just multiply how many ways each part can be done, multiply those together. And that's a nicer way you can do this without having to actually list them all out. Now, there's this little special note. This principle only applies if the number of choices for any particular part is the same no matter which choices were selected for the previous parts. This is called the uniformity criterion. In other words, back to George's example, if for one of the shirts he didn't have 3 possibilities for pants, this wouldn't work. A direct route anyway. Each particular part has the same number of choices no matter what. So for his green shirt he has 3 choices for his pants. For his white shirt he has 3 choices. Okay, we'll talk about that more, but there is a uniformity criterion for this to work out. I also like to call this the blanks method, because if you just do a blank for each part, like on George's case, shirt, pants, and then shoes, you've got a blank for each method, so I like to call it the blanks method. Just fill in the blanks is one other way you can think of it. Okay, so question 1 here. How many ways could George choose an outfit then of shirts, pants, shoes, and hat? So he's added to his wardrobe here. He's got 6 shirts, 5 pairs of pants, 3 pairs of shoes, and 2 hats. Well, no need to go through a tree diagram. There's no need to list all these out. How many do we know he's going to have? Well, if he's got 6 shirts, 5 pairs of pants, 3 pairs of shoes, and 2 hats, how many is that going to be? Multiply those together, 180. He's going to have 180 different outfits at hand he could wear. Okay? So let's multiply those together, and you got it. Fundamental counting principle. Okay, question 2. Richard, George's cousin, has 8 shirts, 4 pairs of shoes, and 4 pairs of pants, and 2 pairs of shoes. One of the 8 shirts, though, is red, and one of the 4 pairs of pants is green. If Richard decides he will not wear his red shirts with his green pants, can we determine the number of possibilities using this multiplication here, and why or why not? Well, obviously not. That's why I've brought this question here. But the reason why not? Why can't we do that? Well, let's think about it. All right, so he has 8 shirts. For this to work, then he would have to have 4 for every one of those 8 shirts for this to work. But is that true? Does he have 4 for each one of these shirts? No. If he's not going to wear his green pants with his red shirt, for the red shirt, he has only 3 options. You see what I'm saying? So is it 4 or is it 3 here? That's the thing you run into if you have some restriction like that. Yeah, you can't do it this way because sometimes it's 4, but then another time it's 3. So you can't just say 8, 4, 2. You see what I'm saying? What you'd have to do is break it up into two groups. You could do it that way, but no, you can't. You can't do 8. It's not going to be 8 times 4 times 2 here, because on one of the possibilities here, there's only 3 for that second blank. Okay? All right. Now, let me scroll up here. Okay, so for the coin problem, this explains then why if 3 coins are flipped, there's 8 possible ways. Because if you put a blank for each coin, think about it, there are 2 possibilities for each coin, right? There's 2 heads or tails for the first coin, there's 2 for the second coin, heads or tails, and then there's 2 for the third coin. So there's 2 possibilities for each coin. What's 2 times 2 times 2? That gives you 8. And we listed out all 8 of them a moment ago. But we can also use this fundamental counting principle to do the same thing. Okay, so that then allows us to do more coins. What if I did 5 coins? Flip 5 coins. How many possibilities are there? Well, if I've got 5 coins, I've got 5 blanks. How many possible for each coin? 2 possible for each coin. 2 for the second, 2 for the third, right? Fundamental counting principle says multiply those together, which is what? How many is that? It's not 12. It's 2 times 2 times 2. How many? 32. 32. Now, the other thing to note here is the exponential. I could write this or do this with an exponent, couldn't I? That's 2 to the 5th power. 2 5 times is 2 to the 5th power. So I could also get 32 that way if you wanted to put it in as a power exponential. Okay? This also explains why if a 2-digit number made from the digits 0 through 3, we did that problem earlier, right? 2-digit number, 0 through 3, there are 12 possibilities. Since we're making a 2-digit number, we need 2 blanks. So if you're doing how many every digit number, you do a blank for each digit. Okay, now why does it turn out to be 12? Well, how many are there possible for the first blank? Remembering we want a 2-digit number, so what can't the first digit be? First digit can't be 0. So how many possibilities are there for the first blank? There's 3. 1, 2, or 3. The second digit could be 0, so how many possibilities are there for the second blank? There's 4. So 3 times 4 gives you 12. Okay? So you can do that with this blanks method too, the fundamental counting principle. So let's go on here to question 4. How many 5-digit numbers are there then using the digits? I just randomly picked some digits here. 0, 1, 3, 4, 6. I left out, 2 and 5 and 7. But anyway, how many 5-digit numbers could you make out of those digits only? So I want a 5-digit counting number. So that's 5 blanks. Why my pen is not cooperating here. Blank for each digit. How many possible for the first blank? Using those digits. 1, 2, 3, 4, 5, 6. Why not 7? Can't use 0 on the first blank here. With me? 6. How many though for the second blank? You don't need 6 blanks. We're doing 5 digits. Yeah. So the number of digits equals the number of blanks. So I only need 5 blanks. The first one though can be 6 possibilities. There's 6 possibilities for this because it's these. 1, 3, 4, 6, 8, 9. But what about the second digit? How many possible are there for the second digit? Well, can the second digit be 0? Second digit can be 0, so we can do any of those 7. What about the third digit? Can it be 0? Can it be 1? Yeah, it can be any of those 7. The rest of them are 7s. Fundamental counting principle says multiply those together, which again, if you want to do exponential, would be 6 times, 7 to the 4th power. You don't have to do it that way, but if you wanted to, you could. Be a little quicker. 6 times 7 to the 4th power, 14,406. With me on that? Question or concern? Question 5 then. How many 6-digit counting numbers are there? Any digit could be used. No restriction on the digits. How many blanks? How many blanks on this one? Well, if it's a 6-digit counting number, you want 6 blanks. Okay. Okay? How many possible are for the first blank? Well, since I can use any digit whatsoever out there, except in the first blank I can't use 0. How many possible numbers are there for that first blank? How many? Well, the digits here we're talking about are 0 through 9, right? Question 5. I can use any of those digits, 0 through 9. However, the first one can't be 0. So how many is that? 1 through 9, which is not 8. That's 9, yeah. There's 9 possibilities. 1, 2, 3, 4, 5, 6, 7, 8, 9. What about the second blank? How many possibilities are there for that second blank? Well, it can be 0, can it? So it could be 1 through 9 or it could be 0. So how many is that? That's 10. How many for the third blank? Third blank can be 0, could be 1, could be 2, could be anything through 9. That's 10 again, isn't it? The rest of them are 10s. Multiply those together. 9. And then 10 5 times. What do you get? 900,000. Right. Right. We don't have, we're just on our numbering system. Yeah. If you're thinking other bases, no, we're not going to do any other bases other than base 10. So yeah, we're restricted on our numbers for digits 0 through 9. All right. Well, let's go to the electing the officers. When choosing a president and secretary for Club Z, the Rachel, Steve, Tina, Vicky was our club, there was 12 possibilities. We choose the president first and then select the vice president. All right, so that's 2 blanks. Why is it 4-3? Well, we've got 4 possibilities for the first. Let me do it right here. Explain it right here for this one. How many possibilities are there for the first officer? If I'm electing the president first, I mean, it doesn't matter which order you go, but we did the president first. How many possibilities could they elect a president? Well, it's these, right? Rachel, Steve, Tina, and Vicky. So there's 4 possibilities for president. However, since no one can serve more than once at a time, it's not 4 here. Because let's say Rachel was president. How many possible are there? 3. If Steve is president, 1, 2, 3. There's only 3 there. So for the second blank, you see it goes down by 1 because you can't have the same officer twice. Instead of 4, it goes down to 3. 4 times 3, which gives me 12. Okay? So that's a little, if you can't have those repetitions, that's what it comes down to, boils down to. If you can't have the repetitions, then this number is going to have to go down as you go. All right, so let's change our club. Our club has expanded. We have 15 members now. And we're going to elect a president, a secretary, and treasurer. How many blanks? 3 blanks. All right, so you need a blank for each office. How many possible for the first blank? 15. Any of those members could be president. We're not restricting anybody. What about the second blank? It's going to have to go down to 14. Why? Because you can't have a repetition. Whoever's a president here can't be elected again here. So there's only 14, isn't it? That rules out one person goes down by 1. Now what about the treasurer? How many possibilities are there then for the treasurer? Well, we're coming out of this, so whoever's here can't be again elected here, so aren't we going to have to go down by 1 again to 13? So 15, 14, 13, multiply those together, 2,730. They can do officers a lot of ways. Okay?